Alright, this video we're going to talk about the concept of a mole. There's an activity that goes along with this video, so if you have not completed that activity, please pause the video now and answer the questions on that activity. They're meant to guide you towards understanding the concept of a mole a little bit more straightforwardly. Okay? If you have completed the activity, let's go ahead and continue. Alright, so this picture shows a mole of several compounds. Okay? So you can see in the center here we have a mole of mercury. Right? Mercury is a liquid. It tends to be very dense, so the actual volume of material is relatively small in comparison to the other samples. Okay? So the amount of the volume that's taken up by 1 mole of a compound is going to depend on the density of that substance. But all of these samples contain the same number of atoms. Okay? So what is the mole? The mole is defined such that it gives us the exact number of atoms that would give us exactly 12 grams of pure carbon-12. This isn't a very realistic situation. You would never have an entire mole of purely carbon-12, but it's just how we've defined the number. So because this is our definition, a mole of anything is going to be 6.022 times 10 to the 23rd units of that thing. So you don't have to have a mole of atoms. You could have a mole of molecules. You could have a mole of electrons. You could have a mole of protons. You can have a mole of anything you want. Okay, and it's always going to be 6.022 times 10 to the 23rd. So a mole of carbon atoms is going to have a mass of, or is going to have 6.022 times 10 to the 23rd carbon atoms, which is a mass of 12.01 grams. That 12.01 grams comes directly off the periodic table. And the reason why it's not 12.00 is because in reality we have isotopes of carbon. So let's just take a second and look at the numbers on the periodic table again real quickly. So if we look at the periodic table, we've mentioned this number before as being the mass number. So the mass on the periodic table represents two different things at the same time. It represents the average mass of a single atom, right, in AMUs. So a single oxygen atom is going to have a mass, an average oxygen atom is going to have a mass of 19.994 grams, or AMUs. Sorry, let me say that again. The average oxygen atom is going to have a mass of 15.9994 AMUs. This number also tells us about the mass of a mole of oxygen atoms. So a mole of oxygen atoms is going to have a mass of 19.9994 grams per mole. Okay, so that number, depending on what unit it is, represents two different things: the average mass of an atom, or the mass of a mole of atoms. Okay, so we can calculate out. So just a quick example: if we wanted to calculate out the number of atoms in 4.48 moles of iron, we could use dimensional analysis. So we start with 4.48 moles of iron. We know that for every 1 mole of iron, we have 6.022 times 10 to the 23rd iron atoms. So we remember dimensional analysis, we have a unit both the top and the bottom of a fraction. They cancel out. Our final units are going to be iron atoms. And when we solve this, we get 2.70 times 10 to the 24 iron atoms. We should think to ourselves, does this answer make sense? We have more than a mole, so our value is larger than Avogadro's constant. It's a very large number because atoms are very, very small. Okay, if you want to put this number into a calculator, you could do 4.48 times 6.022 e to the 23rd equals. So that way you don't have to deal with parentheses or multiplication for the exponential. So you should learn to use this E button on your calculator. Okay. So molar mass. Molar mass is just the mass of 1 mole of a substance. Okay. So if you look at the periodic table, 4 Nitrogen, you see that the mass of 1 mole of nitrogen atoms is 14.00 grams per mole. The molar mass of H2O is 18.015 grams per mole. You'll notice this terminology, so a -1 exponent is the same as taking the reciprocal. So grams, this grams times moles to the -1 is the same as grams per mole. To find this 18.05 number, you simply multiply the molar mass of each atom times the quantity of that atom and add them up. So we have 2 hydrogens. Each one has a molar mass of 1.0079, so 2 times that mass plus the molar mass of an oxygen atom gives us the molar mass of water, which is 18.015. The molar mass of barium nitrate is 261.34. So these parentheses here are telling us that we have 3 nitrate units. So a nitrate unit is 1 nitrogen and 3 oxygens. So this molecule contains 1 barium, 2 nitrogens, because we have 2 nitrates, each nitrate contains 1 nitrogen, and 6 oxygens. To find the molar mass of barium, the molar mass of nitrogen, we have 2 of them because 2 nitrates, and the molar mass of oxygen. So this value times 2 times 14 plus 6 times 15.99 is going to give us the molar mass of barium nitrates. So a quick multiple choice question. So which of the following 100-gram samples will have the greatest number of atoms? So please take a second, pause the video, and solve this question. Okay, so hopefully you should realize that we need to think about the molar masses of each of these to figure out which one has the greatest number of atoms. So since moles and atoms are directly related, we can just look at the periodic table, look up the molar masses, and we should be able to figure out which one has the most atoms. One thing to note about sig figs from the periodic table, you should always think about what other measurements or what other things you're thinking about in a problem when you decide how many sig figs you're going to pull off the periodic table. So in this case, since we're comparing atoms that are relatively far apart on the periodic table, we really don't need many sig figs at all in order to solve this question. Okay, so magnesium has got a molar mass of about 24 grams per mole. Chlorine has a molar mass of about 35 grams per mole. Zinc has a molar mass of about 65.39 grams per mole. And silver has a molar mass of about 108 grams per mole. So if we just look at these numbers, it means if we have 100 grams of sample, we have less than 1 mole of silver, we have more than a mole of all of the other ones, and then whichever one has the smallest molar mass is going to lead to the largest number of moles. Okay, so magnesium has the largest number of moles because it has the smallest molar mass, so therefore it will have the largest number of atoms. Okay. Another question, rank the following from smallest to greatest number of atoms. So please pause the question and take a second to answer it. Okay, hopefully you realized you don't have to do much math at all for this. So if you look at the values on the periodic table, we have about 1 mole of silver, because the molar mass of silver is 107.9 grams per mole. Molar mass of zinc is 65, so that means we have more than 1 mole. And the molar mass of magnesium is 24.3 grams per mole. So since we have 20 more, that means we have less than 1 mole. So if we rank these from greatest to least, it's going to go more than 1 mole. So zinc is greater than silver, which is 1 mole, is greater than magnesium. Okay? So you should always think about when you're solving problems that you don't need to do math on every single problem if you can avoid it. In this case, just by comparing the numbers to the molar mass, we could determine if we had more or less than a mole, so we could rank them based on that. Okay, as the last example, let's say we have 100 grams of each of the following samples, so just water and carbon dioxide, and the question wants us to rank them from greatest to least in terms of oxygen atoms. Okay, so in this case, we can do some more dimensional analysis. So we have 100 grams of each substance, so 100 grams of H2O. We know that for every 1 mole of H2O, the molar mass is 18. Now remember, in this problem, we're not calculating out a value, right? We want to just rank them from greatest to least. Therefore, it's not very important for us to use a lot of sig figs in this molar mass, right? So we have 18 grams per mole, and then we know that for every 1 mole of H2O, we have 1 mole of oxygen atoms. Okay? We don't have to go any further to calculate the actual number of atoms because we can just compare number of moles. So again, if we have more moles, it means we have more atoms. So we can go ahead and just calculate out the number of moles of oxygen. When you multiply that out, you get 5.55 moles of oxygen atoms. We do the same thing, so we have 100 grams of carbon dioxide. For every 1 mole of carbon dioxide, we have 44 grams per mole. Now, for every 1 mole of CO2, we have 2 moles of oxygen. So remember, this subscript is telling us that for every carbon dioxide, we have 2 oxygens. So therefore, we can calculate this out, and we're going to calculate 4.56 moles of oxygen atoms. Okay. So even though each carbon dioxide has more oxygen atoms by itself, we have, because the molar mass of water is so much smaller, we end up with more moles of oxygen atoms in the water. So our ranking would be, from greatest to least, would be H2O. It's going to have more oxygen atoms than carbon dioxide.